In this video, we're going to talk about the section 6.4 in our book. It's the Fundamental Theorem of Calculus, Part 2. So to kind of set the stage for this, we want to consider the idea of constructing a function from an integral. We'll also call this an integral function. So if you consider the yellow curve here, the horizontal line y equals 3, then if we say that capital F of x is going to be the integral from 0 to x of f of t, that is, for reasons to make this actually make sense and work, we can't have these variables be the same. So since we're choosing x to be in our limit, then we're going to choose any other letter we want to be the integral, the variable of integration in our integral. So I just have chosen t. That's done pretty typically, but it can be anything other than x. It doesn't make sense if you have the same variable in the integrand and in the limit. So at any rate, if we think of this now as kind of an accumulation of area function from 0 to x, then capital F of 0 means we would integrate from 0 to 0, and we know that the area under a curve from 0 to 0, or the integral from 0 to 0 of any function, is going to be 0. So that tells us that capital F evaluated at 0 is 0. And when x is equal to 1, that means we're going to look at the area under the curve from x equals 0 to x equals 1. And so we can see that's going to be a rectangle that's 3 by 1. So using an area argument, we could see that capital F evaluated at 1 is 3. Similarly, capital F of 2, we're going to get the area under the curve from 0 to 2. That's going to be a rectangle that's 3 by 2, and that's going to be 6. So you can see that this function we're defining as an integral really does depend on x. You pick different numbers for x, and you get different values for capital F evaluated at that number. Now we can actually, in this case, find an antiderivative of 3 with respect to t would be 3t. When we evaluate that using our first fundamental theorem of calculus, we would plug in the upper limit and minus the lower limit, and so we would get just 3x. So that is, we're saying capital F of x, we can actually write an equation for that, and it would be 3x. Now we're going to be looking at this in many different scenarios because we're trying to see kind of a pattern of what's happening here. That's going to be the part of the fundamental theorem of calculus. Part 2 is going to have to do with how we take a derivative of this function defined as an integral. And you can see the derivative of 3x is just 3, which is in fact the same as the integrand was on the integral function. So in some sense, differentiating cancels out or removes that integral. And we're just kind of planting seeds there. So let's suppose we define a new function now, capital G of x. And this is going to start at a different place than capital F did. Capital F was looking at what's the area accumulated under y equals 3 from 0 to whatever we choose for x. And the function capital G of x, our starting point is going to be x equals 1. So when we evaluate capital G at 0, we're going to find the area under the curve from x equals 1 to x equals 0. Now we can see that's the rectangle is 3 by 1, so the area is going to be 3, but because our limit here is going from a bigger number to a smaller number, that is, we're taking the integral from 1 to 0 of f of t, then that is going to be a negative 3. G of 1 is going to be the integral from 1 to 1 of f of t, and the integral from 1 to 1 of anything is 0. G of 2 will now get this area from x equals 1 to x equals 2 under the curve, and that's going to be positive 3. So we can actually do this integral as well. So to get an equation for a capital G of x, rather than defining it just as an integral, we would again get 3t. This time we're going to evaluate that from 1 to x and get 3x minus 3. So g of x, our equation, is 3x minus 3. So you can see it's different by a constant than our capital F of x. But its derivative, since the derivative of a constant is 0, the derivative of g prime of x is still the same as the derivative of capital F. Okay, let's try this now in a more generalized sense. So now if we say capital H of x goes from any number a to x, then we could still integrate this. So to get an equation for capital H of x, we would get 3t, that's the integral of our 3 with respect to t, and we would evaluate from a to x, and that would be 3x minus 3a. So this is our capital H of x. So you can see that it's got a constant that's being subtracted from our 3x, but the constant won't matter when we take the derivative. The derivative is going to be the same. Okay, so trying to establish a pattern here that we're going to get to and formalize in a moment. Now let's take a function that's a little more complicated, a cosine function. So first let's imagine, like we did, we're going to try to evaluate this function f of x at different values of x, making an area argument if we can. So here's our cosine function in the green on the right. The integral, f of 0 is going to be the integral from 0 to 0 of cosine of t, and the integral of anything from 0 to 0 is going to be 0. And I don't know if you remember, we've talked about this a little bit, but if you remember the area, if we had the full loop, that area would be 2. So the area under a half of a loop of a sine or a cosine curve is actually going to be 1. And that's not critical. We'll get that. We'll see another way of getting to that in a moment. F of pi would mean, I think you can see visually here, we would be going, so this is pi over 2 and this is pi. We would get the area under this curve that's above the x-axis plus that equal area below the x-axis, so we would be back to 0. Now, let's see if we can actually find out what f of x is. So if we actually integrate cosine, we know we'll get sine of t, and if we evaluate that from 0 to x, that would give us sine of x minus sine of 0. Sine of 0 is 0, so our function, f of x, is just sine x. That's the equation of that function. And of course we know then the derivative of sine x is cosine x, and notice that's exactly the same as the integrand that we started with. Okay, now suppose we did this not necessarily just from 0, but from any number. So if we consider the lower limit to be any number a, then the integral, again, of cosine is going to be that sine of t evaluated from a to x, and so that is going to give us sine x minus the sine of a. That's our actual equation of that function that we were thinking of as being defined as an integral. We can see its derivative. The derivative of sine is going to be cosine, and the derivative of any constant will be 0. And so again, we see our derivative is the same as just plugging in the x into the integrand. Okay, now if we can generalize that and understand that, I'm going to come back to this one in a moment. So here is our actual fundamental theorem of calculus part 2. It says that what we're going to get when we differentiate a function defined as an integral from any constant 2x is going to be just f of x. Hopefully that's making sense. We've seen that pattern emerge from what we've done before. We want to use this. The power of this fundamental theorem of calculus part 2 is doing something like the one we see here. Now, sine of t squared is one of these integrals that we say does not have a closed form solution. That is, you nor anybody else can write down a function whose derivative is sine of x squared or sine of t squared. But we can still, this is a continuous function, so we can integrate it. As we can find the area under that curve from whatever value we want to start to whatever number we want to go to. So this is still, we would say, an integrable function. And so even though we can't write down specifically what that function is, we can define it as an integral. This is our function, the integral of sine of t squared dt from any number you like to x. Now, its derivative, what we have seen, is going to be, in a sense, the derivative peels away that integral sign. It's going to just be our integrand function with the x plugged in where the t was. That is the derivative for this function f of x defined as an integral. That's what the fundamental theorem of calculus part 2 is saying. It gives us a way of, well, we have a new way now of defining a function that even if we can't actually write down what an antiderivative of that is, we can still treat it as a new function, and we still know what its derivative is going to be. If we want to evaluate that, we're going to have to use our calculator and use that numerical means of plugging in different numbers for x, kind of like what we did here, where we could see and make the area argument with how to evaluate these different functions. Our calculator gives us that ability when it gets more complicated and we can't actually just look at it and tell how to make an area argument to evaluate it. Okay, see if this makes sense. This is usually kind of a hard idea for beginning calculus students to grasp. So here's our function, f of x. Now this is another example of a function that does not have a closed form integral. So you cannot write down a function, nobody can, whose derivative is going to be e to the x squared. But we can still define a new function as its integral, and we can find its derivative using the fundamental theorem of calculus. We're going to just plug that x in, and its derivative will be e to the x squared. Remember, it doesn't matter what that constant is, because if we could have written down what that antiderivative of this was, when we evaluate it at a constant, that is going to be just a number. When we turn around and differentiate it, that derivative of a number will be 0. Okay, see if we can try another one. So, to differentiate this, we're going to just get the tangent of x cubed. That is the derivative of this integral function using the fundamental theorem of calculus. Now, there's some twists and turns to this. It gets a little bit more complicated. So the first complication is, notice, now the x is appearing at the lower limit and the constant is the upper limit. So we know that you can do this a couple ways. If you just know that if you could have written down what that function was, the antiderivative, you would have evaluated that at the upper limit minus evaluating that at the lower limit. And then when you turn around and differentiate that, the derivative of the constant would be 0, and then we're going to get a negative capital F prime of x. That's going to be a negative secant of x squared. We're just plugging in that x into the integrand, but it's switched the order, so that's going to be a negative. Alternatively, we could say correctly that the integral from x to 3 of any function, I'm going to do it more generally, of any function is going to be the negative of what we get when we switch the order of those limits. And so we know that the derivative of this from the fundamental theorem of calculus will be f of x, and then we have that extra negative, which is where that negative is going to come from. Okay, now let's work through this first. I'm going to do this because I've brought back an integrand that we can actually integrate. I want to do this. Notice how complicated our limits have become now. They're actually functions. So what I'm going to do here is actually find the antiderivative, evaluate it at the upper limit minus the lower limit, and then I'm going to turn around and take its derivative. And we'll notice what's going to happen, how that chain rule is going to apply to these integral functions, so that we can then do it when we have integrands that we can't actually find an antiderivative for. So it looks something like this. We know the integral of cosine is sine. I'm going to evaluate that at the upper limit minus the lower limit. So that's going to become sine of x squared minus the sine of 3x. This is what we're calling f of x. So in this case, I can actually do this integral and evaluate it. Now, what we want to know is what is f prime of x. And we're going to work through it here, but then we'll notice how to do this when we can't do this in-between step of actually figuring out what the antiderivative is. So when we differentiate f, we're going to get it's a chain rule, so we're going to get the cosine of x squared times the derivative of x squared, which is 2x. Okay, see, there's the chain rule part. Minus, we're going to get the cosine of 3x times the derivative of 3x. This is how we're going to do that chain rule. So when the limit is a function, it's more than just x, then the chain rule, the derivative, is going to have the derivative of the limits as part of the final derivative. See if this makes sense. Here's the yellow one. So we can't integrate this. We can't find an antiderivative of that. It doesn't exist, doesn't have a closed form. But we can still take its derivative, this integral function. So we're going to plug in the x cubed, so that's going to be 5 raised to the x cubed squared is going to be x to the 6 times the derivative of x to the third, which is 3x squared, minus, I'm going to plug in the 2x. 2x quantity squared is going to be 4x squared, times, from the chain rule, the derivative of 2x is going to be another 2. This is the derivative of this integral function. Okay, see if you can do this next one. So, taking its derivative, we're going to plug this in. So its derivative is going to be the natural log of x squared plus the natural log of x. All that goes in the radical. Then we're going to multiply that by the derivative of natural log x, which is 1 over x. Minus, we're going to plug in the sine x. So that's going to be the sine squared of x, sine of x squared, plus the sine of x. All that is in our radical. And then the chain rule part is going to be times the derivative of sine x, which is cosine x. This is going to be our derivative of that integral function. Now, there's another twist on this. This is kind of like the fundamental theorem of calculus 2.5. So it's not really a separate part of it, but it's an application of this fundamental theorem of calculus. It allows us to construct a solution to a differential equation. So you can't use this in general because we will solve lots of differential equations, and in general we're going to want you to find that actual function whose an integral, whose derivative is given. But in some cases, like in this one, we can't find an integral of this. So we can still construct a solution to it. We're going to say our function is going to be, and then we're just going to write integral function here. So I'm going to say from a constant a to x. I'm going to come back to that a in a moment. And then I'm going to say the cosecant of, and then I have to change the variable and go t cubed dt. I'm not finished yet, but this is a start. Now, from what we've learned about the fundamental theorem of calculus, we know right now that f prime of x, the derivative of this, is going to be, that's where we just plug in the x, it's going to be cosecant of x cubed. Well, that's exactly what I wanted. That's a solution to this differential equation. Now, the next part I have to do is to make it satisfy the initial condition. We want f of negative 2 to be equal to 11. Well, there's a clever way we can do this. I'm going to choose this a to be that negative 2. So now, as I have it written, the derivative is still going to be cosecant x cubed because that constant isn't going to change anything. But right now, what we have is that f of negative 2 is going to be the integral from negative 2 to, and I would plug in negative 2 where the x is, of this cosecant of t cubed dt, and we know that the integral from a to a of any function is just 0. So right now, this function is 0. I want it to be 11, so I will just make it 11 by adding in that constant that I want. Now, does that 11 change the derivative? No, because the derivative of that constant is just 0. So f prime of x still is exactly what we want. It's going to be that cosecant of x to the third. That satisfies the differential equation. Does f of negative 2 equal 11? Well, when you plug in negative 2 into our function, we're going to get 11 plus the integral from negative 2 to negative 2 of cosecant t cubed dt. Well, an integral from a to a is 0, and that makes f of negative 2 11. It works. This is exactly what we want. It kind of seems like cheating, but it's a kind of foolproof way of finding a solution to a differential equation. Now, is this actually usable? Well, yeah, because now if I wanted to, and you will sometimes be asked this on AP questions or maybe a test question, if I wanted to know what is f of 5, well, then we would just grab our calculator and we would get our 11 plus the integral from negative 2 to 5 of cosecant of t cubed dt, and we would evaluate this part using our calculator and the numerical integration feature, and then we'd have the plus 11, and we could find f of 5 or f of anything that we want. So it is actually a trick that is useful, that can help us. Okay, see if you can try this one. You might want to pause it and do it on your own. Otherwise, I'm going to jump in. We're going to say that our function is going to be, we're going to start out by defining it as an integral. We're going to go from pi to x of, and I'm going to call that tangent squared, and I have to change the x to something other than x. I'm going to choose t, but you can pick whatever your favorite letter is other than x. Right now, we have created a function whose derivative is what we want. And now I want, but it's right now at f of pi, it's going to be the integral from pi to pi is 0. I want it to be e squared plus 1, so we'll just add in the e squared plus 1. And this function satisfies our differential equation. All right, very good.